Yeah, so I would like to thank the organizers for the invitation. And let me begin by introducing one of the main tensions in the standard cosmology, which is the Hubble constant, the tension in the Hubble constant. And I'll focus mainly on the strong gravitational lensing and the lensing of gravitational waves. And try and understand what promise they hold in this context. So as we know that the standard cosmological model can explain plethora of observations, and yet there are many unresolved mysteries. For example, we don't have very good understanding of the nature of dark matter and dark energy, even though they comprise the dominant budget of the energy budget of the universe. And as with growing precisions of various observations, we are now starting to see tensions and inconsistencies in different probes. And one of the most important ones is this tension in the Hubble constant measurement. This is mainly the tension that is seen between the early universe probes, for example, CMB, and the late universe probes like the cosmic distance ladder measurements. So just to explain a bit more, we measure these temperature fluctuations from the CMB, which arise from the underlying density fluctuations, and we can infer the cosmological parameters such as the Hubble constant by fitting a cosmological model to these angular power spectrum of these fluctuations. The latest measurements we have are around 67.4 from the Planck collaboration for the H0. And on the other side, we have the distance ladder measurement from the late universe, which comprise of Cepheids and supernovae, which are standardizable candles, and they allow us to directly measure the distances and thereby measure the H0. And the latest measurements from the SHOES collaborations, they are around 73.2, and you can see there is this significant differences between these two probes. So there are, of course, many more probes that you may be aware of or have heard in the previous lecture, but I'll focus mainly on the another very completely independent probe of H0 measurements coming from strong gravitational lensing. So let me see if I get, yeah. So what we expect is that the background distance source, when it is sufficiently well aligned with an intervening galaxy in the line of sight, we can see multiple images of the background source. And these multiple images, they traverse different geometric paths. They also experience different geometric potentials, which then introduces time delay between these multiple images. And so Revsdahl in 1964, he suggested that if we can measure these time delays, then with the help of these d delta t factor, we can constrain the Hubble constant, provided we can characterize the lens mass model, or and we have also the redshift measurement in these systems, which is the redshifts of the foreground object and the background object. So we can get a measurement of these Hubble constant with the help of these time delay measurements from these strong gravitational lenses. So initially, Revsdahl had supernovae in mind. However, as luck would have it, there were lots of lens quasars which are around, which are much more easily accessible, and they also have intrinsic variability, because of which you can actually measure these time delays. And so historically, people have been looking at the time delays of lens quasars and using them to constrain the Hubble constant. So this has been religiously, let me also start this animation where you can see how the intrinsic variability in this 4-image system of a lensed quasar, you can see the intrinsic variability, and you can see here at the bottom how the light curves are measured over a period of several months. And you can then look at some features, specific features in these light curves to determine the time delays between the multiply lensed quasars. So this has been religiously studied by the two collaborations. One was Holy Cow, which was then succeeded by the TD Cosmo collaboration. So the fiducial model that the Holy Cow collaboration had, it constrained the H naught up to a very few percent precision, which then indicated a phi sigma tension with the early probes of the H naught. And then more recently, from the TD Cosmo collaboration, they revised their models and took into account various systematic uncertainties. There are various known degeneracies in the lensing analysis. So they have taken those things into account, and based on the revised models, the error bars on these H naught measurements have relaxed, and now the more recent measurements, they are much more in consistency with the existing probes. So right now we can't really say whether there is a tension between the early and the late probes of the H naught. So these lens quasars are a really good way for measuring the H naught via the strong lens systems. One of the pros for these particular analysis that they have undertaken are that these collaborations, they try to do the analysis in a blind manner, which minimizes the confirmation bias. And I think there are more and more probes or different teams who are doing these kind of measurements should include this kind of methodology where you are blinding your analysis so that you don't try to get an answer that you expect to find in your from your data. And so the other thing, as I mentioned, that these are variable sources and they are always there, so they are easier to find. However, the cons, one of the biggest disadvantage of these methods, I would say, are that the monitoring observations are extremely time intensive, and one also need to do very accurate photometry to get very accurate measurements of the time delays. So this can be a big disadvantage. So coming back to the lens supernovae, which was initially.
You were talking of blind observation. Exactly what are you blind to? That is.
So it's the analysis that is done in a blind way, which means what.
You analyze for one image, you completely ignore all information.
No, so the way in this particular collaboration, one of the things that they are doing is that this d delta t measurement, that there is some random value which is added to this d delta t, so that you don't know beforehand what you should expect based on the redshifts and other information. So there's a constant offset that is added. Yeah, and then there's an unblinding that happens where you're not allowed to then go back to your tools and fix anything. So that sort of thing is what they do. Yeah, so bringing back the lens supernovae. So only in the last few years that we have started to now discover these lens supernovae. That now again there is all this interest in making use of these lens supernovae for time delay measurements and cosmological measurements. So there have been a handful of these lens supernovae. So of course, any lens supernovae would be good enough, but the icing on the cake is that if you have lens supernovae of type 1a, then these are already standard candles. And because of their lensing and the time delay measurements, there are additional constraints that these type 1a supernovae bring. So the type 1a supernovae, we know the intrinsic luminosity, and because of strong lensing, there is this magnification factor that is added. In any other type of source, you cannot really know what this absolute magnification factor is between a true source and the lensed images. But for type 1a, you can determine what is this absolute magnification. And so this allows you to put additional constraints and break certain model degeneracies that exist in the lensing analysis. And so that's why using lens supernovae of type 1a are going to be very interesting. And at the moment, I think we have only one and maybe another, I think there is only one or two lensed supernovae of type 1a that we know in the literature. So this field looks really promising. As I mentioned, the pros are that this is a standard candle. The other interesting thing is that because it's a transient, after a while, the supernova source will disappear, which leaves you with this once all these supernova images disappear, you are left with these only extended arc-like images of the background host galaxy, which are much cleaner to measure the positions of the arcs and make much more much stringent to get much stringent constraints on the mass model. And so this is an additional advantage compared to the lens quasars, where the quasars are always there. And so the disadvantages of using lens supernovae is that there is microlensing, which is there are the lens galaxies. They consist of all these stellar populations, of course, which have the right size to cause further perturbations in the fluxes of these supernova images. And this is the microlensing effect. So on top of the strong lensing magnification, you have this unknown factor that gets added, and that factor is different for each of the different supernova images. And so this microlensing brings all this extra uncertainties in your model, because of which it gets really hard to use these lens supernovae as standard candles. And the other things is that if these supernovae are located in massive galaxy clusters, then the mass distribution of these galaxy clusters can be really messy. And in that sense, it may not be as ideal if you want to use it for cosmology. So just to summarize, there are these tensions in the H0 measurement. The questions are there problems with any particular probe? Are these analyses suffering with confirmation bias, or does this really hint for the presence of new physics? And I think there's going to be a talk toward the end of this workshop where you'll hear more about this. So I'll just summarize here that there is this tension, and so this motivates for having other independent probes for H0 measurement. And so that brings me to the topic of gravitational waves. So the Einstein's predictions for gravitational waves, they came true from the first direct detection of the binary black hole system in 2015. The gravitational wave sources are expected to arise from different phenomena, starting from the inspirals of compact binary coalescence, which is what we detected. But there are other processes like stochastic processes in the early universe, or continuous emission from binary or isolated sources, or just bursts which are expected to arise from unknown sources. These are all the different types of gravitational waves emissions we expect to see in the data. So the compact binary coalescence, these are the systems where you have either a pair of neutron star or a pair of black hole, or a neutron star and a black hole in a binary system. And such a binary system, they emit gravitational waves, which causes the orbit to decay, resulting in a merger, followed by a ring down of the leftover black hole. And this kind of a system, or the signal, can be very well determined with the help of these intrinsic parameters like the masses and the spins, and also the extrinsic parameters like the luminosity distance, the sky localization, inclination, and so on. So just for the sake of completeness, gravitational wave sources directly act as standard sources, standardizable sources. So here they are called standard sirens for obvious reasons. So the idea is that if you have a binary neutron star or a neutron star and black hole, which can have an electromagnetic counterpart, which means you can identify its host galaxy in the EM data, and thereby get a measurement for the redshift. And if you then combine with the luminosity distance, which you can measure from the signal, the CBC signal itself, then you can directly get a measurement of the H0. And this was indeed shown with this GW170817 system, which was the first binary neutron star that was discovered. And there was an extensive follow-up in the EM community, which allowed us to narrow down the host galaxy in which this BNS was located. And then obviously people have then tried to get the H0 measurement from this one system alone. And you can see from this plot here, this curve that shows the H0 measurement from GW17 over 17 with these vertical shaded regions. They serve as a reference coming from the Planck and the Schulz collaboration, and you can see that these measurements are consistent with the previous measurements.
Binary neutron stars are standard siren, but if you have a one neutron star and one black hole, how is that a standard candle?
It's on the basis of the fact that if you can get the redshift.
Yeah, but
and the luminosity distance from the shape of the signal itself. From the shape of the signal, the frequency evolution of the signal that gives you an idea of the chirp mass, and from the amplitude.
That you could do for any two black holes also, right?
Yeah, but you won't have the redshift from the EM counterpart. Yeah.
If you locate the galaxy, and then you can do this for any two objects, any two black holes. For instance.
Right. If you could, yeah. But that's not possible for BBHs. And so, in fact, but there are other methods that are, oops. Yeah, there are other methods that are proposed which make use of dark sirens, which is not directly finding the exact EM counterpart, but still making use of the EM galaxy catalog. So the idea behind this is that if you have a merger, and if based on the sky localization, you have some set of galaxies from which have redshift from the EM catalog, and you can get a distribution of the H0 for a given merger, right? And then you can combine this with hundreds of mergers, and statistically, then you can get constraint on the H0. So that's another way of making use of these GW sources as dark sirens. So there are many such studies which have explored different methodologies or improved this initial idea by Schutz et al. And so here I'm just showing this one plot which comes from the LIGO collaboration, making use of the latest catalog where 47 events have been used. And again, these vertical shaded regions are the Planck and the Schulz measurement, and these are various measurements considering different like the BNS separately, and all the BBH sources and so on. So now let me move on to the gravitational lensing of gravitational waves. So just like the lensing effects that you see in the EM, we expect to see similar effects in the gravitational wave domain also. So specifically, if we think about the strongly lensed systems of these CBC sources, then what we expect to see in the data are multiply lensed events. They will appear after some time delay, and these events, they will have different luminosity distances because of the different lensing magnifications. There will be also a phase shift between the different types of images that are seen in the typical lens system. These systems will appear to come from the similar direction in the sky, and they will also have similar masses. So the main lensing observables are the time delays, the relative magnifications, and phase differences. So in order to better understand what we expect to see in the data, so for the record right now, we don't have any known lensed gravitational wave that has been detected in any of the gravitational data so far. But there have been many studies to understand what are the lensing rates that we expect in the current and the upcoming detector sensitivities. And also many methods have been developed to look for the presence of strongly lensed events in the data. So let me just begin by motivating based on the lensing rates. So we have calculated these lensing rates for lenses which are produced either by individual galaxies or the massive galaxy clusters. And then for the background sources, there is quite some uncertainty on the BBH population themselves, like what are their mass functions, what are the merger rate and their evolutions and so on. So we explore these different models and then determine what are the lensing rates. So roughly we find that in the optimistic case, we expect 1 in 1,000 events to be lensed, strongly lensed by galaxies, and very similar for by galaxy clusters. So for the current detector sensitivities, it's really difficult because we don't really have that many gravitational wave sources detected. But in the next few years, we definitely expect to see detection of strongly lensed gravitational waves. But one should also remember there are always these observational biases that if there is some extremely magnified event, then it is easier for us to detect it. And there is a good chance that we might see such extreme event in the next observing run as well. So I also want to quickly mention that one of the things that we can readily do once we find these lensed events is that we can turn the problem around and constrain the merger rate density models, because these merger rate density models, they sensitively depend on the number of lensed events that we expect to see. And so at the moment, we have put constraints on the basis of non-detection of the lensing events. But in the future, we'll be able to get better constraints once we start to see some lensed events.
Ratio 1:1000. Is it different? What is it for EM?
For the EM, it's also very similar. But in the EM, we have like many imaging surveys, so we have easily found them. Things change a little bit based on what you assume for the background population, but it's roughly 1 in a few hundred or 1 in a few thousand is the sort of rates.
So 2 events in the same direction within a magnitude of, let's say, a year would be a candidate for a lensing.
A year is a bit too long. I mean, it's not impossible, but you can get that with galaxy clusters. We are talking about even shorter time delays, like a few weeks.
So if you analyze the signal and just pick pairs within a few weeks of each other in the same direction, and that's a candidate for lensing.
That's a very roughly, you can use that sort of.
How do you say they are actual lensed events or they're different events?
Yeah, so I am going to talk about that now. So I'm going to quickly talk about some of the methods that people have used for identifying strong lens candidates. I'm just going to focus on just a couple of them, and we can talk about others later perhaps. But the main idea is that because of strong lensing, what we expect is that there will be a single, let's say, binary black hole source, which will be lensed by a foreground galaxy. Then you will have events that are separated in time, but the masses of these events should be the same, and they should be coming from the same direction. So intrinsic parameters should be similar. So what some of these rapid techniques that are used, what they do is that every event that has been detected from the standard pipelines in the collaboration, they have already performed some sort of parameter estimations, and we have idea for the posteriors of various binary black hole parameters. So what they just do is that they look for overlap in the posterior distributions of these parameters. So this kind of method is called the posterior overlap. So for example, this B overlap quantifies how much is the overlap between the parameters of the binary black hole. And for lensing, there would be a significant overlap compared to any just random pair of unlensed events. So that's this B overlap. Then there's also this R-gal factor, which makes use of the fact that the time delay distributions are actually very different if you have a population of lensed events versus, again, unlensed events. So that's quantified by R-gal. And so they make use of this B overlap and R-gal to determine what are the promising candidates of strongly lensed events. And this plot here then shows the efficiency and the false alarm probability for different models. So I'll talk about this a bit more in the next slide. There's another method, for example, which is using machine learning. And this makes use of visual information. So for example, you can look at the frequency versus time spectrograms, and the chirping binaries, they have a characteristic shape. So that depends on it depends on the mass of the system. It depends on how long the signals are, how the frequency evolution happens, and so on. So this is again very characteristic. And so if you have two lensed events which are, if you have two lensed events, then they will look very similar to each other, whereas random pairs of unlensed events will not show those similarities. So this method makes use of these two-dimensional images and looks for similarity in these signals.
Just have a question. So how does this compare to quasar microlensing, like the statistics, like in the 100 megaparsec cube volume? Are there more quasars or more gravitational wave binary mergers that you would expect? Like if I just want to know compare the statistics.
So I don't think we have, so at the moment we have not very good understanding of the merger rates of the binary black holes, especially at those high rate, high redshifts. I mean, we have some idea, but we still, the total number are still in the, only in the order of 100. So we don't really have a very good idea of how the rates are. The lens quasars, it's not a transient source, right? Binary black holes are still transient. So lens quasars, they are there all the time. So it is much easier for you to find lens quasars observationally than to find lensed binary black holes.
Yeah, so I mean, just given the statistics that you have many more quasars
Yeah.
and probably many more lenses, so isn't it more likely that you'll see quasar lensing? And so the statistics of, we already have very few systems where you have quasar lensing and the time delays are like years, right? There, why the time delays here weeks? It seems.
No. Even for lens quasar, it's the same for galaxy scale. So it depends on the mass of the lens. So if you're talking about, let's say, galaxy scale lenses and the typical redshifts that are involved, the time delays that you see are over weeks to months to years. It's not that there is any difference between the time delays of the lens quasars versus lens PBH.
Okay, but holy cow, most of the delays are years, right? Like holy cow measurements, all the delays are several years.
They may they're not delays. There is a monitoring observations which they have to do to, in order to measure the variability over a long period, so that they can identify certain features with which then they can quantify the time delays. The time delays are few weeks or months. Sometimes the time delays can be even days. But the monitoring observations have to be done over a long period because of various reasons, the telescope not being available, or it can be like you can monitor for 2 years, but there is no obvious feature in the variability. It's all random. So you cannot make use of such data to quantify the time delays. That is the issue. That these, if you want to use lens quasars, it is very time intensive. And you have to make sure that you're getting very accurate photometry all the time. The cloud conditions and everything are very good. So observationally, it is much more difficult. So it's much more painstaking. Whereas for lensed BBH or lensed DW sources, time delays are something that you get instantly and extremely accurately. Also, I'll mention that in the next few slides.
Yes, then lens supernova is also.
Exactly. Exactly. Yeah. So in that sense, lens supernova are much better. You don't have to worry about, monitoring observations and all that, but it also has other issues. So yeah, I'll come to that. So so here I'm showing the results from the lensing paper from the LIGO collaboration, where this B overlap versus Argal is shown, and these different data points are different pairs of events. Which are candidates for strong lensing, and these different contours, they show the typical population, just the random population of events. And so if you have if your pair of events, they lie in this top right corner, then they are good candidates for strong lensing. And as you can see, there is hardly anything that crosses these contours. So very recently, what we proposed is another improved method on top of this Argal, because in this Argal, what they were doing is making use of only the time delay distribution. Whereas what we are proposing here from our recent work is that we should use something called MGAL, let's say we call it MGAL, which makes use of the joint distributions of the various lensing observables, like the time delays, the magnification ratios, the phase shifts, and so on. And so we have demonstrated this here with these plots here. So we can see that on the x-axis are the relative time delays, and then the relative magnifications, and each of these plots are for different types of the images. And these shaded regions, they show the random population of unlensed pairs of events, whereas these green contours, they show where the lensed event pairs lie. And overplotted are these blue data points, which are the candidates from the lensing papers. And you can see that there is this one particular candidate, which according to our analysis is basically coincident with the lensing population. And so this particular candidate is same as what's shown here, which has a relatively low R-gal. So it gets an R-gal value of 8. If we do the analysis by using time delay only, we also get a value of around 8. But if we make use of this joint information, then that boosts the significance of this particular event pair, and this would then push this this event pair to rightwards. So this just demonstrates that you can do a much better job of identifying true lens event pair if you make use of M-gal instead of R-gal. So this is something that now we are incorporating in some of these analysis. We have also gone a step forward. I'm sorry. We've also gone a step forward and did a few more systematic studies to understand what is the impact of making the choice of a specific lens model for the galaxy population. And so very briefly, what we find is that if we make no assumption, then we have this background of unlensed population shown by this blue solid curve. And then the lensed population is shown by these dashed blue curves. So there is quite a bit of this overlap region where the event pairs could be either lensed or unlensed, and there is no way to tell. But if you make use of either the time delays or the magnification ratios and the time delays going from the green to red, you can see that the overlap between the background population and the lens population reduces, and it just shows that it only helps if you make assumptions for the lens model and make use of these joint distributions instead of ignoring them. So talking about the motivation, the scientific motivation here. So we can do cosmology with lensed gravitational waves, very similar to what I discussed before, like lensed quasars, lensed supernovae. So in this paper by Liao et al., they did some mock analysis to understand and compare how lens GW can better with respect to lens quasars. So they, for example, they have listed here the various uncertainties in the model. So the uncertainties in the line of sight contribution from the mass in the line of sight is going to be very similar for the lens quasars and lens GWs. But if you look at the uncertainties in the time delay measurements, then it's essentially zero, because we have very accurate measurements of the time delays. There is also some improvement one can get in the lens mass model compared to the lens quasars. So here they have shown this projected constraints. If you have 10, let's say 10 lensed GW systems where the EM counterparts have been identified, and then how much better the contours are compared to if you have just lens quasars. So as I was mentioning, for lens GWs, you don't require to do any sort of monitoring, and you can get extremely accurate time delay measurements. The disadvantages that you need to have the not only the EM counterpart correctly identified, you also need to identify the GW counterparts. This may seem as a surprise or non-intuitive, but the correct identification of the subsequent GW counterparts is also an extremely important challenge, which can affect this kind of analysis. So okay, yeah, so I think I started a little bit late, maybe. Okay, okay, all right, okay. No, okay, I'll go quickly.
This will get us H0.
Okay, so yeah, so very quickly then there have been studies which try to understand how difficult it's going to be to identify the correct EM counterparts. And this plot just shows with decreasing localization area on the sky, the fraction of systems that can be correctly identified, and it seems to be on the lower side right now. So it just needs much more better techniques to be explored and made use of. So another just very quick result I wanted to point out is that there are a few studies which have also identified that without actually using the EM counterparts, we can again do this statistically by looking at this joint information of time delay distributions and the abundances of lensed events to get constraints on cosmological parameters. So In terms of cosmology with lensed binary neutron stars and NSBH, where we can identify an EM counterpart, we have looked at the lensing rates, and it looks promising that in the next few years we will be able to find lensed binary neutron stars. We have also looked at the time delay distributions to see how well advanced in time we can make predictions for when the next images of the lensed counterparts will appear, both in the gravitational wave data or in the EM data. And this can be of the order of hours or days. And this can be extremely important if you want to study the BNS themselves. If you want to look at the initial stages of the BNSs, then this kind of early warning studies can be very important. There's another study where they have looked at the observational feasibility. Takes time. It's gone. Okay, there's another study where they have looked at the observational feasibility, and what they suggest is that if we look at the mass gap, the gap between the neutron stars and the black holes, then that is an efficient way of selecting candidates to be followed up in the EM. In this analysis, they have also looked at typical models for the EM counterparts and looked at their light curves and how bright they are going to be as a function of the time. And for example, if you look at the Rubin LSST telescope, which is going to do a survey, what sort of observational times will be required and whether they'll be able to detect these kind of counterparts, lens counterparts. And what they suggest is that if we can follow up within a matter of a few days, and if we can do sufficiently deep pointing, we'll be able to detect some of these candidates. So I want to talk about the microlensing, and we can maybe discuss later if there are questions. But I wanted to highlight this effect of microlensing, which arises from these stellar populations located within the lensing galaxies. The lens supernovae themselves are very much affected by these microlensing effects because of the small sizes of the background sources. Coming to gravitational waves, these are even the intrinsic sizes of gravitational wave sources are even smaller, so they are definitely going to be affected by microlensing effect. What is even more complicated here is that we are now looking at a slightly different regime because of the wavelengths of the gravitational waves. So in the EM, the kind of time delays and the kind of EM frequencies that we look at, these are this factor is much greater than 1, and you can operate in the geometric optics limit where the lensing magnification is just a single factor. Whereas in the gravitational waves, it happens so that you have to take into account diffraction and interference effects, because of which the lensing magnification factor is a function of the frequency, not just a single factor. And so this is something that we have characterized in our first paper by Mishra et al. He is a PhD student who has implemented this framework where we can determine what is the microlensing amplification factor as a function of the frequency, and you can see how these distortions occur as a function of the frequency. You can see that at higher frequency we can see much more distortions because of the microlensing, and how this can impact the lensing of gravitational waves. So for that we also did a study where we looked at the probability of seeing microlensing, where we have explored the entire density range of the microlenses and the strong lensing magnification factor. So we have looked at the range which is less than magnification of 10 here. And what we find is that in almost all cases, if the strong lensing magnification factor is less than 10, then the microlensing effects are small enough that you cannot distinguish them from typical just any unlensed event. So that's what's shown here by this match percentage. If the match is really good, you cannot distinguish between an unlensed versus a microlensed event. And so what the takeaway from this is that for all the systems where the magnification is less than 10, almost all of these lens GW events, even if there is microlensing, they will not affect your detection or parameter estimation. But the number of such events in the upcoming observing runs are going to be 50%. So 50% of the events can have very high magnification factors, which means they can have very high or strong microlensing distortions. And so this is something that we need to worry about and take into account. And so we are also now trying to understand the effects on the parameter estimation because of these highly magnified systems. So with that, I would like to leave the summary slide here and take any questions.
Thank you, Anupreeta, for that excellent talk. We have two quick questions. Yeah, go ahead.
Hi. So I had kind of a naive question. What is chirp mass? I'm not exactly familiar with the terms.
The chirp mass is the mass that you can infer by looking at the frequency evolution of the signal.
Right.
Yeah, we can.
That we should observe in order to have the accuracy of H0, which is, let's say, matches with shoes.
So as I showed with this, I mean, we don't have any study that has been done to do a realistic projection, but the one that I showed was this paper where they talked about what you can do with 10 lensed GW systems where the EM counterparts have been identified.
I see. I see.
So there's also a table which actually lists the constraints. So you can, it's a few percent, which is what they mentioned. But again, it's in a very, in idealistic conditions, I would say, if you start taking into account some of the systematic issues, then it can be slightly more. Yeah.
Okay. Okay.
Thank you. So we'll take the remaining questions in the present session. Thank you, Anupreeta.
Thank you.